Hi, welcome to CS50x by Ahmad. This is the first video of week 0. Computer scientists like to start counting from 0, so at CS50 we thought we should apply the same to weeks as well. Week 0 is the first week of the course, and this is the first video of week 0. In this video, we will be going through an introduction to computer science, a very important introduction. So let's get started. The first thing that I would like to discuss with you is the definition of computer science. Unlike most people think, computer science is not about programming, at least not about programming alone. It is mainly about problem solving problems using computers. Okay, so what about programming? Programming is just a computer science tool, like many tools we use in computer science to solve problems. Okay, if computer science is about problem solving, what is problem solving? Problem solving is something that humans do since the beginning of time, since Adam and Eve. Humans had problems and still have problems since the beginning of time, and they are solving, at least most of them. So if I say, for example, what is 1 plus 1? That is a problem that I need you to solve for me. So maybe hopefully you will say 2. So if you think about this very simple problem, 1 plus 1 equal 2, you will find it looking like this. We have some inputs, some information about the problem at hand, and we are looking for a solution or an output. So hopefully we will take inputs, the information that we have about the problem, operate on them, perform some operations on these inputs, and then come up with the output or the solution. Okay, now humans are greedy. They always want to do things faster. They always want to do things more accurately. And this is why they invented, for example, the wheel. So they were moving stuff and they were moving people and animals from one place to another place, but they were having a hard time doing that. So they came up with the brilliant idea of the wheel. And the wheel solved the problem for them. It made the problem much easier. So now they can move stuff faster. The same applies to the invention of steam. The whole industrial revolution is based on steam. So using steam, again, we can solve problems faster and more accurate. So how is this related to what we're talking about? Actually, this is the reason that we invented computers in the first place. Okay, we need to do stuff faster. We need to do stuff more accurately. And this is why we invented computers. Now, it is the time that I tell you the story about Alan Turing. If you watch the movie Imitation Game, you know what I'm talking about. If you didn't watch the movie, watch it. Although I will be giving you some spoilers here. So who's Alan Turing? Alan Turing was a British mathematician during the World War, the Second World War, who invented a device, okay, or invented a machine. And remember this word very well, the machine. He invented a machine to crack the encryption of the German army. Now, the story was the Germans were using some sort of encryption to encrypt their communications. So the British cannot know what they're communicating about. So the British Army, they brought a group of mathematicians in order to solve this problem or try to decipher or decrypt this encryption. However, at that time, we didn't have computers. There were no computers per se. So these mathematicians were trying to solve the problem manually using pen and paper. However, Alan, he started thinking this is not going to cut it. This is not a good solution. Why? Because the Germans are changing the encryption every 24 hours. And we, humans, cannot break this encryption in 24 hours. We are slow and we make mistakes. So he decided to invent a machine, create a machine, and use this machine to basically do whatever humans are doing, solve the problem in the same manner, that humans are following. However, the machine is going to do it faster and in a more accurate way. And he was successful. Now, here's the question. Why is the computer more faster and more accurate than a human? Is it because a computer is more intelligent? Absolutely not. It's simply because a computer is a machine. Like I said, it is dedicated to the job. A machine, like a car, does not have feelings. It doesn't get tired. As long as you operate within its limits, it's never going to have these emotions. It's never going to say I'm tired, or it's not going to make mistakes. So this is basically why do we use computers to solve problems, and that's the essence of computer science. Okay, now the question is, how can a machine solve problems? Okay, humans can solve problems. How can a machine solve problems? We understand that we can have a machine like a car taking us from point A to point B, but solve problems, actually, it's not a big gap. The car, although it's not like a computer, but it is solving a problem, right? So you want to move from point A to point B, you can move on foot, but you will do this like slowly. Or you can take a car and you will do this in a much faster way. So if you think about it, the car is actually solving a problem for you. However, the problems that we would like the computers to solve are far more complicated than that. So we need to answer this question. How can a machine solve problems, complicated problems? Now, you need to think of computers or machines like a baby who's learning. So assuming that we have a baby, just a very small baby. This baby, when it is born, it knows nothing. But we teach the baby, right? In order for us to teach the baby, you need to know how to input the data first to the baby. So you don't ask baby to solve problems right away, but you try to feed information to the baby first. Teach the baby how it can, he or she can accept information first and process this information, and then later on you teach the baby how to solve problems. So our main issue here is not the whole problem solving process, but this part of problem solving, which is how are we going to input information to this machine? This machine is just a piece of plastic or a piece of metal. How are we going to get information and then feed that information into the computer? And let's worry later about how is it going to use this information to solve a problem. In order for you to teach a baby or a computer, which is worse than a baby actually, so the baby at least has a brain. Yes, when the baby is born, it knows nothing, but it has a brain. The computer does not have anything. It's just, as I said, it's just a piece of metal or a piece of plastic, and you need to input information to that piece of metal or a piece of plastic. So we can use the same strategy that we use with babies. And in order for you to teach a baby the basics, you need to understand the basics. Okay? You cannot start communicating with babies like talking about politics or talking about complicated mathematical formulas. That's not going to work. You need to go from the absolute basics. So one of the very basic things of human knowledge is numbers. So the numbers and the counting system is something very simple, and it's the whole human knowledge is based on numbers. We're using numbers every day, okay? Almost every second of our life. Okay, so what about numbers? What about the counting system? The first system that I would like you to know about is called the unary system. And it's coming from the word una. Una means one. So the unary counting system uses one symbol. For example, a finger. So if I tell you now, count on your fingers, so you have here your fingers, and then you start counting. So we're going to say 1, 2, 3, 4, 5, etc., right? So this is a very basic counting system here. And this system is using the finger, and the finger is one symbol, so we're only using the finger in order to count. So if you take a look at this finger here, how many fingers do we have? We have 5, but all of them are just one finger. So you can, here, using one hand, you can count up to 5, starting from 1 to 5. So the unary system looks like something like this, and it's very, this is something ancient. So the ancient people, they used to engrave these vertical dashes, if I may call them, on stone and bones in order to count numbers. If you are teaching a baby, for example, you can use your fingers, or you can use something else, again, using one symbol. So you can say, for example, apples. So bring one apple and say, this is 1, 2 apples, that's 2, 3 apples, that's 3, and so forth. Again, you're using only one symbol here. What about counting from 1 to 10? Can you count from 1 to 10 on your fingers? Yeah, absolutely, because I have 10 fingers, and I can, let me see, here, 10 fingers, and I can count from 1 to 10. Again, using the only symbol that I have, which is the finger. How to count more than 10? If I want to count more than 10, can I do that? Yes. Using fingers still. Maybe use the fingers in a different way, right? So I have only 10 fingers, but I still want to count more than 10. So maybe I can start doing something like this and say, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's counting 10 on one hand, and I can do the same thing on the second hand, okay? Or I can use the finger up, finger down, so do something like this. So this is 1, this is 2, this is 3, this is 4, this is 5, and you can keep doing something like this. So this is basically manipulating this one symbol into 2 symbols, for example. So I can use the finger up, this one here, finger up is 1, finger down is 2. So I'm not very happy with this unary system, and we will talk about that in just a minute. Why are we not happy with the unary system? So I started thinking maybe I can use the same symbol, but in different ways. Now this moves us to the current system that we're using, which is called the decimal system. The decimal system gets its inspiration from the unary system, okay? But we don't want to use only one symbol. It seems like one symbol is not enough, and it has some problems, as we're going to see in just a minute. So we started thinking, why use one symbol if we can use 10 symbols instead of the 10 fingers that we have? So we start using these symbols, so starting from the 0, and in the decimal system we have a 0 to represent basically nothing. And then 0, 1, 2, 3, 4, 5, 6, 7, 8, up until 9. So these are 10 symbols, and using these 10 symbols, we are going to count numbers like we did in the unary system, but in a better way. So how do we count more than 9? It seems like we start at 0, and then we count all the way up until 9, but then I want to count more than 9. And this was the same question that I asked you here, how to count more than 10. Because I'm not limited to 10, right? I have, yes, 10 fingers, but when I'm counting, I'm not limited to 10. So I need to see how am I going to count beyond 10. So the same question applies to decimal system, how to count more than 9. In this particular case, we use the pattern of 10 symbols instead of the flow of just one symbol. What do I mean by that? Now, let's take a look at this table here. These are decimal numbers that we use currently in our everyday life. And this is the unary system. In the decimal system, we use the 0 to represent nothing. And in the unary system, we didn't have anything, like there was no symbol for that. So if we just leave things empty, that means nothing. In decimal system, we use the 1 to represent 1. And here we use the single dash, right? If you take a look at the 2, now the 2 is basically changing the symbol. So here I have the symbol, that's the 1 symbol, but here I'm not using this symbol twice like I'm doing here in the unary system. I'm just changing the whole symbol completely, using a completely different symbol that looks like this, which is the 2. The same applies, for example, to the 3 and to the 9. In the unary system, I'm using a flow multiples of one symbol because I have only one symbol, right? But in the decimal, I have multiple symbols and I can switch between these symbols. However, as soon as we get into the 10, actually, the unary system, it doesn't have a problem here because it will just add one additional vertical dash. That's what it does. But in decimal, I'm using a pattern of these 10 symbols. I'm out of symbols from 0 to 9. I'm out of symbols. So what am I going to do? I'm going to construct a pattern of symbols next to each other. I'm going to take the 9 and convert it back to the 0, which is the beginning of the cycle. And then next to the 0, I'm going to put a 1, and that is representing the 10. In this particular case, the 1 doesn't actually mean 1, and the 0 doesn't actually mean 0, right? This whole number here means 10, okay? So when you take these symbols and you put them next to each other in a pattern, they mean something different than if you take a look at them while they're alone like this. So yeah, after the 10, we go to 11, and then we go to 50, and then we go to 100. And now you start seeing why did we substitute the unary system for the decimal system? Because you see 50 here, in order to represent a 50, I can just put two symbols next to each other, like the 5 and the 0, and this is going to give me 50. But if I'm still using the ancient unary system, I need to put 50 dashes next to each other. That's too much. You see how long that is? If I want to move to 100, for example, I didn't even have space. So I just put like these dots. 100 would be too long if we're using the unary system. Okay. Now, let's take a look at how this decimal system works, okay, in detail, because this is important. I know that you know this from school. This is something that I'm sure that you have studied when you were still young, maybe in grade 1 or something. But let's revisit this and have a refresher of this concept, because we will use it later in computer science in a more important context. Okay, so let's start with the counting. We start counting in decimal. We started counting from 0, right? 0 basically means nothing. After the 0, we use the next symbol, which is the 1. Then we use 2. And then we keep going. After the 2, 3, 4, 5, 6, all the way until the 9. But then, as I said before, we run out of symbols. So what are we going to do? Here's what we're going to do. We will substitute this 9 with the 0. Why the 0? Because this is the beginning of the cycle. We started counting at 0, right? Okay, so we will substitute the 9 with the 0, the beginning of the cycle. Then we will add a new place to the left of that. Now, this is the 10. However, when you add a new place to the left of the 0, you don't put 0 here. I know, I said that we started counting from 0, but you know what? 0 next to 0 means nothing, right? It's like it's 0 after all. So in order for that to make sense, we need to start the new place to the left, the second place, this one, we need to start that from 1. And now it will make sense. As I said, 1 here doesn't mean 1, 0 here doesn't mean 0. This is a pattern of symbols. 1 next to the 0, to the left of the 0, it means 10, which is the number after the 9. Okay, so what's next? What's next is that we keep cycling. This place here, the one that we converted to 0, the beginning of the cycle, it will continue the cycle. It will go 1, okay, making the number 11, and then it will go 2, making the number 12, and so forth all the way until 19. But once again, we are out of symbols. We exhausted all the symbols that we have. Yeah, we know what to do now. We will take this 9, convert it to 0, back to the beginning of the cycle, and then move to the second place to the left. We already have a number here, so we can increment that number by 1. So now it will become 20. Once again, the 2 here doesn't mean 2. The 0 here doesn't mean 0. The whole pattern, 0 with the 2 to the left of it, it means 20, which is the number after 19. Now, if we keep doing this, we will eventually reach 99, right? And then we will be out of symbols for both of them. We're out of symbols here and we're out of symbols here. So what should we do? Very simply, convert this to 0, convert this to 0, add a new place to the left, and put 1 in that place. The new place always starts from 1, which is basically the 100. And then again, after the 1,000, the 100 are going to have 1,000 and so forth. Okay, I know it's boring because we already know that. What are you? This is a Harvard course. Why are you teaching stuff from grade 1? Now, bear with me. We know that this place here is called the ones place, correct? We studied this in school, early school. And this one is called the 10th place. And then this one is called the 100th place. And this one is called the 1000th place. And why do we call them these names? We call them these names because, as I told you, a 0 here doesn't actually mean a 0. And a 0 here doesn't actually mean a 0. Okay, the 0 here doesn't mean a 0. The 1 doesn't mean a 1. They have different meanings now in this pattern. So let's go ahead and take a look at this number, 3,719. Okay, no, hold on. What did I just say? 3,719. This is the correct way to pronounce this number, right? Okay. Why did I say 3,000? Where did I get this 3,000 from? I get it from the fact that the 3 is actually in the 1,000th place. And if the 3 is in the 1,000th place, it doesn't actually mean a 3, it means 3,000, right? The same applies to the 7. Does this 7 mean a 7? No, it means 700. Where did I get this 700 from? I got it from the fact that it is in the hundreds place, and if it is in the hundreds place, it means 700. And the same applies to the 1. The 1 here doesn't mean 1, it actually means 10. And the 9 here means 9 because it's in the ones place. So what we're doing is that we're basically multiplying. I'm sorry, let me okay, so we're basically multiplying this number by this number. So we're doing 9 multiplied by 1, 1 multiplied by 10, 7 multiplied by 100, and then 3 multiplied by 1,000. Okay, if you think about it, it's basically after the multiplication, we add them together like this, and it's going to be 3,000. And then 700, and then 10, and then 9, that is 3,719, which is the number that we started with. So this is basically where the number 3,719 comes from. We put the symbols not next to each other, and each place has its own value, okay? And the number takes the value from the place. So the number multiplied by the value of the place, that is the total value for this number in this place. And then we keep adding these values together to come up with the 3,719. Okay, very good. Now, here's the thing. What I would like to do with you is to understand where these numbers are coming from. Like, who said that this should be the ones place? Who said that this is the 10th place, or the 10th place, or the 100th place, or the 1000? Where is this actually coming from? Okay, are we just doing it because we like to do 10 and 100? Actually, no. This is coming from the fact, and this is maybe something new to you that you didn't study at school. This is coming from the fact that the 1 is actually 10 to the power of 0. And the 10 is actually 10 to the power of 1. The 100 is 10 to the power of 2. And the 1000 is 10 to the power of 3. So why is that? So why are we doing 10 to the power of 0, 10 to the power of 1, 10 to the power of 2? Okay, let me discuss this with you. This is very important. The reason we do, let's start with the base. It seems like all of them are having the base 10. So let's start with the base. Why is the base, why are we using 10 in the base? We're using 10 in the base because we have 10 symbols, right? Remember? So how many symbols do we have in the decimal system? The decimal system, actually the first part of the word decimal, dec, means 10, okay, in Latin. So dec means 10. And the reason that we are calling it decimal, starting with dec, is because it has 10 symbols, remember, from 0 to 9. So basically, in the decimal system, each place, the value for the place, will have the base of 10 because the whole system has 10 symbols. Okay, very good. And remember, we will always call this decimal system the base 10 system. As you can see, all the places that we have here, the ones, the tens, 100s, and 1000, all of them are coming basically from the fact that the number 10 as a base is raised to a power. Now, let's talk about the power. Where's the power coming from? No, there's no rule here. There's the rule for the power is very simple. It's that we start counting at 0 and we increment by 1. So the first place here is the base of the system, which is 10 to the power of 0, because we start counting from 0, right? And then here it's going to be 10, because the base is constant across the decimal system, raised to the power of 1. Why 1? Because we started 0, now it's 1, then it's 2, then it's 3. And if you think about it, 10 to the power of 1 equal 10. 10 to the power of 2, which means 10 multiplied by 10, that is equal to 100. And then 10 to the power of 3, that is 10 multiplied by 10 multiplied by 10, that is actually 1000. Okay, so let's take an example here. Before we take an example, there's something very important that I need to discuss here with you. This exponential method that we're using, which is base to the power of something, is basic. We can explain that in a simpler way, which is the multiplications of 10. So when we start the 1, and we can say, yeah, 10 to the power of 0, 10 to the power of 1, etc. But we can also say that in a different way. We can start with a 1 and then multiply by 10 every time. So 1 multiplied by 10, that's going to be 10. 10 multiplied by 10, that's going to be 100. 100 multiplied by 10, that's going to be 1000, and then 10,000, and so forth. So many ways to express the value of each place in the decimal system, as I said. All of them are coming originally from base 10 to the power of the series of numbers from 0 to 1 to 2 to 3, etc. But we can simply express them as 1, 10, 100, 1000, or you can say 1 multiplied by 10, 10 multiplied by 10, 100 multiplied by 10, so every time you multiply by 10. Another thing, before we get to the example, is a very important question. If I have something like this, if I tell you that I have 3 places, only 3 places. So here, as we can see, the number 3710, this is a 4-place number. It's taking 4. We need 4 symbols next to each other. But if I say this, if I tell you that you are limited only to use 3 symbols only, Okay, what is the maximum number that you can count to? You can say, okay, I'm going to start from 0 or 0, 0, 0, and then I will keep counting 1, 2, 3 all the way until 999. Correct? To the maximum, so the maximum number that you can count to in the decimal system using 3 places only is 999. Okay, here's another question. How many numbers were you able to count, total numbers that you were able to count? Actually, you were able to count 1,000 numbers because, yeah, the maximum number that you can count to is 999, but there is a 0 at the very beginning, right? So in total, you were able to count 1,000 numbers using these 3 places. And there is a rule for that I want you to learn, because now this, again, it seems easy. If I ask you this question, you will answer right away because it's very easy for you to do. But we need to understand where is this coming from, because we will ask this question again later, and it's going to be more challenging to answer unless we know the rule behind it. So where's this 999 actually came from, or where's the 1000 came from? It came from 10 to the power of 3. 10 to the power of 3 is different from this one now. We're talking about 10 to the power of 3 in a different context. Now, what is the 10 to the power of 3? If I ask you, how many numbers can you count? Not the maximum. How many numbers can you count in decimal system using 3 places? You are going to say, in the decimal system, I have 10 symbols, correct? And you limited me to 3 places. So 10 to the power of 3, that is going to equal 1000. So I can count up to 1000 numbers using 3 places in the decimal system. If you want to know what is the maximum number that you can count up to, you simply minus 1, because there is the 0. The 0 is one of the numbers. So you say 1000 total numbers minus the 0. So the maximum that I can count up to is basically 999. I know that this seems very simple. It may seem boring. Okay, no problem. I agree with that. But again, what we are discussing here is going to be very valuable moments later. Okay, so let's go ahead and take a couple of examples here. I would like, for example, to discuss with you the number 139. Okay, so let's apply what we just learned in order to break down this number 139. So what we need to do is that we need to start from the beginning. We need to say 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and then 10 to the power of 3, but we don't need that because there is no number here, right? And then calculate that. 10 to the power of 0 means 1. Anything to the power of 0 equal 1, okay? So 10 to the power of 0 equal 1. 10 to the power of 1, just 10. It's 10 not multiplied by anything. So that's 10. Then 10 to the power of 0. So that is 10 multiplied by 10 equal 100. And then here, this is 1000. But again, we don't need that right now. Then what we do next is we multiply this by this. So we say 10 multiplied by 1. 9 multiplied by 1. 3 multiplied by 10, and then 1 multiplied by 100. So that is going to be 100 plus 30 plus 9. That is equal to 139. Again, I know that we are coming back to the same number, but the process itself, it's very important to understand. So let's try another number very quickly. This number that I'll be using now is 5072. I will basically do the same thing again. 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. I need that this time because I have the 5. And then I'm going to calculate 10 to the power of 0 equal 1, and then 10 to the power of 1 equal 10. Or I can simply multiply by 10 every time. I told you, you can get it from the base to the power operation, or you can simply multiply by 10. Why multiply by 10? Because it's base 10. Because it's a decimal. We have 10 symbols. So each next place is basically the value of the previous place multiplied by 10. So we can keep doing that. So this is 100 or 10 to the power of 2. Multiply again by 10 here. That's 1000, or 10 to the power of 3, which is 10 multiplied by 10 multiplied by 10. Then the next step is multiply here. So 2 multiplied by 1, 7 multiplied by 10, then 0 multiplied by 100, and then 5 multiplied by 1000. 5 multiplied by 1000, that's 5000, right? Then 0 multiplied by anything, that's 0. Then we have 7 multiplied by 10, that's 70, and then 2 multiplied by 1, that's 2, which is again basically 5072. Okay, so enough of this decimal system. It's very simple. I hope that you understand the basics behind the decimal systems. The decimal system, how do we count in the decimal system? How do we calculate the value of each place? It's certainly the most important thing that you understand the base concept, which is if we are in the decimal system, that's called the base 10 system. Why 10? Because we have 10 symbols, and we use that to calculate. As you can see here, the 10 is used, the base is used every time to calculate the value of each place, and the value of each place is going to determine the value of that number in that place, and then we add them together to come up with the final number. Also, don't forget the exercise that I just did about the question of how many numbers maximum can we count up to using a certain number of places. Like if I give you 3 places, how many numbers can you count using only 3 places? And the answer is 1000. As we said, the maximum number that you can count up to is 999. And this, revise that one more time. It's very useful for what we're going to discuss in just a minute. So now the question is, how do we teach the computer? Okay, in order for us to teach the computer, maybe it's a good idea to teach the computer the decimal system, right? That's a system that we're using, and this is one of the very basic things of the human knowledge. So if the question is, can we teach the computer the decimal system? Remember that the computer is a machine. Remember when we're talking about the Turing machine. And Alan Turing, as I said, is the father of computer science. All the computers that we're using nowadays, laptops, desktops, even phones, all of these, or what we call general purpose computers, are based on the work of Alan Turing and the Turing machine that we were talking about. If the computer is a machine, maybe we can compare it to a car. So the computer, it's like a car, but uses electricity. So what happens in a car? Can a car solve a problem? Actually, yes, we discussed this. Okay, the car, although it's not a computer, but it can solve, and it is solving a problem for us. It's taking us from point A to point B in a faster way. And it seems like we can order the car to do something and it obeys the order. So if you step on the gas, the car is going to move. You leave the gas, the car is going to stop, or when you hit the brakes, for example. So it seems like we can teach the the car to do something. And how did we do that? We used the source of energy for the car. So the car does not understand anything except fuel. You give it fuel, it will burn the fuel. This is how it is designed. And the more fuel it burns, the faster it's going to go. And we can control that, or we can teach or command the car to do that by simply controlling the fuel. So if we can use the fuel to make the car understand the concept of moving and stopping, maybe we can use electricity to make computers understand numbers. So can we use electricity to represent numbers? Yeah, maybe. Why not? Let's think of something that uses electricity so we can represent electricity. So in cars, we burn the fuel, and this is something tangible, but the electricity is not tangible unless, for example, we represent it with something like lamps. So when we connect electricity to the lamp is going to turn on. When we disconnect the electricity from the lamp is going to turn off. So we can use series of lamps using electricity to represent numbers like we did in the unary system. You remember the unary system that we started with? How can we represent the number 3, for example, using electricity or using lamps? How can we do that? Um, um, let's take a look at this example here. Okay, so I wanted to represent the number 3 using electricity or lamps in this particular case. So I can bring one lamp, connect electricity to it, and this represents the number 1. And if I want to represent the number 2, I can add another lamp. And if I want to represent the number 3, the number that I want to represent, I can do it like this. This is basically what we did in the unary system, using the lamp as the one single symbol in counting. And if I want to count up to, let's say, for example, 10, I can do the same thing with these lamps. So I'll bring 10 lamps, connect electricity to them, and that's representing the number 10. So it seems like a solution, but it's not a very good solution, because we started having the same problem that we had in the unary system. And this problem is, okay, what if I want to count up to the number 1000? Okay, if I want to count up to the number of 1000, I will need 1000 lamps, and this would be too much. Remember the problem that we had in the unary system? Having 1000 lamps next to each other. That is, it's not the best solution, correct? However, we can get inspiration from fingers. You remember we had this problem with fingers, and then we thought, okay, how can we use fingers in a different way that will allow us to accommodate more numbers using less fingers? You remember when I had my hand like this, and then I started saying, okay, instead of saying 1, 2, 3, 4, 5, I can say 1, then 2, then 3, then 4, then 5, then 6, and so forth. So maybe using lamps in a different way, it's going to solve this problem for us. Okay, we have the solution already from the transition from unary system to the decimal system, which is use a pattern instead of a flow. So instead of a flow of lamps, maybe use patterns of lamps. Okay, so how can we do that? We have a very good example, a very good analogy here, which is the Morse code. I'm not sure if you know about the Morse code, but the Morse code is a way of communication that is used in the military. It's used in aircraft and ships and this kind of stuff. And it uses only 2 symbols to communicate, believe it or not. Those of you who are familiar with the Morse code, they know exactly what I'm talking about. But let's go ahead here and take a look at this website here. So in this website, this is a very nice website. It's called the Morse Code Translator. And what you can do is that you can write whatever you want here, normal English. This is CS50x by Ahmad. And then if you click play, it will basically give you the sound that is used by the Morse code. So the Morse code is using, as I said, only 2 symbols. It's using the dash and the dot. That's it. Can we communicate this as Ahmad said using only 2 symbols? Actually, yes. And the Morse code is using these sound signals. Dash is a long sound signal and a dot is a short sound signal. So let's go ahead and hear that together. How is this is CS50 translated into Morse? Can you hear that? Okay, awesome. So what is the Morse system, or what is the Morse code? The Morse code is basically a dictionary between human letters like A, B, C, and this kind of stuff, and a series or a pattern of just two symbols. So I don't know exactly the translations, of course, for I don't know them, I don't remember them by, I don't know them by heart. So for the A, for example, we have a dot. Then for the B, we have dot, then dash. So it seems like we can communicate using just two symbols if we agree beforehand on how these two symbols are going to translate to something that we can understand. So this is a very good example on how we can do something using a small number of symbols, not necessarily 10, not necessarily 26, like the English language is using 26 letters, but we can do it with far less symbols. So in the Morse, as I said, the Morse is using two sound signals, right? The long one and a short one, to represent the human language based on an agreed like dictionary, as I said. Why not use light signals? Because we're using lamps, right? You remember? In here, in this example, we're using lamps. So why not use the light signals instead? Okay, how can we do that? Take a look here with me at what we can do with these light signals. Okay, what if we use a light bulb that does not have electricity, it's turned off, in order to represent the zero? So I'm going to bring a series of light bulbs or lamps, right? And then instead of having all of them turned on and put like, if I put 10, that means 10. If I put 15, that means 15. Now let me be more smarter. Let me be smarter here. So if I have a light bulb that is turned off, let's agree that is going to represent a 0. If I turn it on, that represents a 1. Okay, now what's next? You remember what we did in the decimal system? We were using a pattern of symbols instead of a flow. So how did we do it? And now you will know why was the explanation of the decimal system, why was it important? Okay, so what should I do next? I'm out of solutions here. So it seems like there are only two symbols that I can use: the turned off lamp, the turned on lamp. But if I get inspiration from the decimal system, I can go back, so turn off this lamp, go back to the beginning of the cycle, which is the turned off lamp, and then put a new lamp to the left that is turned on. And now I can represent the next number, which is the 2. Okay, why not put this lamp turned off? I told you 0 next. We agreed that the turned off lamp means a 0. So if you put two turned off lamps next to each other, that basically means 0, 0, which is nothing. So when you create a new place, like when we did with the decimal system, you start that a new place with a 1, and this is what we're doing here. Okay, so what is next? What is next is that we take this turned off lamp and we turn it on, because we move forward into the cycle. Turned off lamp is a 0. The next stop is turned on lamp, which is the 1. So it's going to look something like this. So that is the 3. And then what about the 4? Actually, we ran out of spaces. So we exhausted everything. Khalas. So what should we do next? And remember, don't tell me that this one should be turned off. The leftmost one cannot be turned off. It has to be turned on, because turned off means 0, and 0 to the left means nothing, right? It's just useless. So we are out of possibilities here. Okay, what do you do when you're out of possibilities? You add a new place. And when you add a new place, what are you supposed to do with these? You turn them back to the beginning of the cycle, which is turned off. So I'll turn this off, add a new one that is turned on, and this is what we do with the 4. Turned off, turned on, that basically means 4. What about 5? That now it's becoming simpler. We turn this one on like this, okay? And the next step is that we take that back to the beginning of the cycle, which is turned off, and then we take that one to the next step, which is turned on, which is the 6. Now, what if we want to do the 7? We can turn this one on, and then we have the 7. What about the 8? Once again, we are out of possibilities, so we need to add one more, one new space, and so forth. This is basically almost exactly what we did in the decimal system. The only difference is that here we're using 2 symbols instead of 1 symbol. I'm sorry, instead of 10 symbols. In the decimal system, we had 10 symbols starting from the 0 all the way to 9. Now here we have only 2 symbols, which is turned off lamp, turned on lamp. Okay, the 2 symbols that we translated into the 0 and the 1. Okay, now what we just did here is a system, an existing system that is called the binary system. So what is a binary system? You remember when I told you about the decimal, dec means 10, bi means 2. Okay, I'm sure that you got it. That binary system means the system that uses 2 symbols only. And these 2 symbols are used in a pattern like the decimal system, but instead of 10, we're using just 2. The decimal system is using a pattern of 10 symbols. The binary system is using a pattern of 2 symbols only. Now, what are these 2 symbols? Yeah, I know that you're going to say 0 and 1, but you know what? 0 and 1, this is just a translation. Okay? It's a lamp that's turned off, equivalent to 0, and a lamp that is turned on, equivalent to 1. However, you know what? We use the lamps only to see electricity, but it's all about electricity in the end, right? The lamp that is turned off is basically a circuit, an electrical circuit that is disconnected, correct? So the switch is turned off. So if we have an electrical circuit that has a switch turned off, or basically the circuit is disconnected, this means the lamp will be turned off. This means the number 0. If we have the same electrical circuit switched on, so the switch is turned on or the electrical circuit is connected, meaning the lamp is turned on, meaning the number 1, that's the second symbol. If you think about this open circuit, closed circuit stuff, you will start understanding what can we do in a computer to input some information. So if I want to input the number 5, for example, yeah, we can go back to these lamps and then we can see the number 5 means this lamp turned on, this lamp turned on, this lamp turned off, for example. And then we put them in a series, respecting the order, okay, and switch this circuit on, switch this circuit off, switch this circuit on, and then we have our number 5 represented just using 2 symbols like we did in the Morse code. Now in the binary system, each of these symbols we call it a bit. The word bit is coming from the term binary digit. Okay, so we take the bi from here and then the t from here, and we call that a bit. So what's a bit? The bit is like any other symbol in any language or numbering system. So in English, for example, how many letters do we have? 26. Did you notice what I just said? How many letters? So what is the term letter? Letter is basically a symbol in English language. So the English language has 26 symbols, and we call these symbols letters. In Arabic, we have the same thing. We have what we call harf. So this is the Arabic name for the letter. In the decimal system, we call the number, right? So 0 is a number, 1 is a number, 2 is a number. So we have 10 symbols, or we have 10 numbers in the decimal system. Same applies to the binary system. We have 2 numbers, or 2 symbols. We don't call them numbers, we call them bit. So the 0, or what it represents, the circuit that is disconnected, this is a bit. The circuit that is connected, or the 1, equivalent to the 1, that is another bit. Only 2 bits that we have in the decimal systems. Now, how can we represent this in computers? I keep saying these circuits and this kind of stuff. So these circuits, and I don't want to get too technical here, we call them transistors. Okay, so in a computer board, like think of it very simply. What I can do here is that I can bring a board, an electrical board. It has a bunch of electrical circuits. You can call them transistors now. And you can switch some of them on, switch some of them off, and then take that and convert it from binary, because this is binary, right? 0 and 1. You can convert it from binary to decimal. Now, how can we do this? How can we convert from binary to decimal and vice versa? Because we need to do that. You can very simply use this here, and you just remember that the one bulb turned off means 0, one bulb turned on means 1, one bulb turned off and to the left of it another bulb turned on, that means 2. But then this is going to be a hectic process, how to remember everything like this, that whole pattern. And if we talk about, for example, the 5, I didn't even remember the 5 when I was giving an example moments ago. So what is a 5? A 5 is basically 3 circuits, okay? One turned on, then one turned off, and then one turned on. However, we have a mathematical way to do this. You don't have to remember. We can use a mathematical way similar to what we used in the decimal system. You remember? The one that was a little bit boring, the one that you studied in grade 1. Okay, we can use the same system, the same mathematical system, that's the reason that I did a refresher on it, to convert the binary to the decimal. So let's see how this is going to work. Remember what we did in the decimal system. We were going to do exactly the same. So we start counting at 0, right? Then we move to the 1. Then we move to the 2. But we don't have 2 in binary, remember? We only have 2 symbols, 0 and 1. So what should we do next? Like we just did here. This is the reason that I have this these light bulbs. So what we do is that we simply convert the 1 to the beginning of the cycle. The cycle is very short. It's just 0 and 1, right? Convert the 1 to the beginning of the cycle, and then add a new place to the left of it, starting with 1. And this is what I just did here. Now, here's the thing. Is this a 10? No, this is not a 10. Okay, this is 2. How did you know? Because this is what we did here, right? So light bulb turned off, that's 0. Light bulb turned on, that's a 1. Light bulb turned off, then next to it a light bulb turned on, that's a 2, right? And this is how we started counting. We started counting 0, 1, then 1, 0 from the left to the right, as you can see here, which is representing the 2, correct? All I'm doing here is that instead of using these light bulbs, because you know what, as I said, we're only using light bulbs to see electricity. But now, since we know that the 0 means a light bulb turned off, 1 means a light bulb turned on, we can just forget about light bulbs and just use the 0 and 1 to represent the electricity being turned off and turned on. Okay, so what's next? This is not a 10, definitely not a 10. This is not a 0, this is not a 1. Not even in the decimal system. As I said, each one has its own value based on the place that it is in. So this is not a 10, this is the equivalent of the 2 in the decimal system. So what's next? We can go forward. So now this is not 11, this is 3, right? And then we have, this is not 100, this is 4, right? So take a look here. If you don't know what's that, turned off, turned on, that is 4. Then we have 5. Then after that, we move that to 1. So this is going to be 6. Then this is 7. So that's, as you can see here, 7 is turned on. What about 8? We didn't do the 8 here, but we can do it now. Now we're out of possibilities. So all of them are now used. So we convert all of them to zeros and then add a new one to the left. That's going to be 1. So we are going to have this 1, 0, 0, 0 from the left to the right. This is not a 1000. This is basically 8. Right? Now, how did I know that this is 8? Let's do what we just did in the decimal system. and give to each one of these places a value. So this one is going to be the 1, this is going to be 2, this is going to be 4, this is going to be 8. Oh, hold on. Where did these numbers come from? In the decimal system, this one's the ones place, tens place, 100s place, 1000s place, right? But now I'm saying something different. I'm saying 1, 2, 4, 8. Where are these coming from? You remember when we talked about the base and the exponent and this kind of stuff? This is basically where this is coming from. So the 1 is coming from 2 to the power of 0. The 2 is coming from 2 to the power of 1. The 4 is coming from 2 to the power of 2, which is basically 2 multiplied by 2. And then the 8 is coming from 2 to the power of 3, which is 2 multiplied by 2 multiplied by 2. Okay. Once again, where's the 2 coming from? It's the number of symbols that we have in the system. In the decimal system, it was 10 to the power of something. Why 10? Because we had 10 symbols. Now we have the base 2 system. Base 2 means I have only 2 symbols, and this means that the base should be 2. And as I said before, the exponent, there's no rule for the exponent. We just start with a 0 and keep incrementing. So 2 to the power of 0, 2 to the power of 1, and then you keep going this way. Alternatively, as we did again in decimal system, in the decimal system, I told you that each place, we start with a 1, and then each place is basically a multiplication of the base, right? So in the decimal system, we start with a 1, then we multiply by 10, or multiply by the base. Then the second is going to be 1 multiplied by 10 equal 10. Then we multiply by 10 by 10, that's going to be 100. 100 multiplied by 10, that's going to be 1000. So it's an alternative way to know the value of each place other than the base to the power of the exponent. We can do the same here. So we start with 1 and then multiply by 2. 1 multiplied by 2 because it's base 2, 2 symbols. So 1 multiplied by 2, it's 2. 2 multiplied by 2, it's 4. 4 multiplied by 2, it's 8. 8 multiplied by 2, it's 16, and so forth. Okay, so this is very good. Now, let's take an example here. The example is going to be this, 1101. This is not 1101. We are not in decimal system anymore. We are in the binary system. However, we would like to know what is this equivalent to in decimal, right? So 1101, how can we convert that into the decimal? Okay, it's easy. What did we do in the decimal system? We took the number itself in each place, and we used, and then we used to multiply that by the value of the place. So we will do this here. So 1 multiplied by 8, 1 multiplied by 4, 0 multiplied by 2, and then 1 multiplied by 1. Okay, and then we add them together, right? So this is going to be what? It's going to be 8 multiplied by 4 multiplied by nothing, multiplied by 0. And then, 8 plus 4 plus 0 plus 1. So this is basically going to equal to 13. So 1101 in binary is equivalent to the number 13 in decimal. If you don't believe me, why don't we do something nice here and open the calculator. So if you're using Windows 10, you can use this calculator in the programmer mode. So take a look at this one here. And from here, you can put this calculator in a standard mode. You can put it in a scientific mode, graphing mode, or a programmer mode. So I would like you to be here in the programmer mode. The programmer mode will allow you to convert between different numbering systems, including the decimal, the one that we use in our life, and the binary, the one that we just learned about. There's also the hex and oct. The hex we will learn about actually in the course later. We will talk a little bit about it also today. There's also, we have the oct system. But anyway, let's just focus on the decimal and the binary systems, as you can see from here. So what should I do? You can click on the deck, this decimal, and then it will allow you to put a decimal number here, okay, which is in our case 13. That's the number that we came up with. And then you can read from here what is the binary equivalent of that, which is 1101. Indeed, the number that we started with, and we wanted to convert to decimal. We did it manually, but on the calculator here, it was done for us. Alternatively, you can do the opposite. So you can click on binary from here. And then if you notice, as soon as you click on binary, it blocks the other numbers. You cannot use the other numbers. Makes sense, right? Because in binary, I only have the 1 and the 0. I don't have anything else. I have only two symbols that I can use. So we can use our the binary number that we started with, which is 1101, and then it will automatically convert that to us into 13, which is the decimal equivalent of 1101. Now you understand the process of this binary system, how the binary system works. It's time for us now to ask the question, the very important question that we asked before. If I give you, for example, 3 places, okay, 3 places. This is the question that we asked in decimal system, you remember? If I give you 3 places and I ask you, how many numbers can you count, total numbers, can you count in binary using 3 places? Okay, what did we do before? We said, okay, the number of symbols that we have, in this particular case is 2, raised to the number of places that we are limited to. So 2 to the power of 3. Now 2 to the power of 3 is what? 2 multiplied by 2 multiplied by 2, that is equivalent to 8. So I can count, if I have only 3 places, I can count total of 8 numbers starting from 0 all the way up to 7, because the 0 takes 1 place, right? Which is, you remember also we did that the total number, number of numbers that we can count is 8, but the maximum number that we can count up to is that number minus 1 equals 7. If you can take a look here, this is basically what we had when we were using the lamps. When we reached, we were able to count 8 numbers, 0, 1, 2, 3, 4, 5, 6, 7, from 0 to 7 maximum. But then we ran out of places and we had to add another lamp in order to count to the 8. But since we're limited here only to 3, that's the maximum. This question may not seem to be useful now, but it will be useful later. Being able to understand how many numbers can I count in a particular system using a particular number of places. So remember this, because we will be using it later. It's always, also to remember this, it's always the base, okay? Base is the number of the symbols that we're using in the system raised to the power of the number of places that we are limited to. Okay, very good. Now let's go ahead and discuss, I'm sorry. Yeah. So how do we convert decimal to binary and vice versa? Now, if I have a decimal number, how to convert it to binary? What we did is the vice versa. So the vice versa, I'm not going to repeat. The vice versa is binary to decimal, and we already did that. 1101, we converted this to 13, and it's a very straightforward operation. The opposite, which is decimal to binary, we need to talk about that in a little bit of detail. So let me go ahead and open the whiteboard. Okay, so now I don't have 1101 that I want to convert to 13. I have something else. I have a different number that I want to convert. I have a decimal number that I want to convert to binary. So let's take, for example, this number, the number 148. So that's a decimal number, obviously, because it has the 4 and has the 8. Yeah, the 1 is a symbol that we have in both binary and decimal, but 4 and 8, this is obviously decimal, right? Now I want to convert this into binary. We have two methods of conversion, okay? One of my favorite, I'm going to start with that. And then there is another method that is more common actually, but it's not my favorite. It's up to you. The first method is called the subtraction method. So what we need to do is we need to put the values. Now I need to take that and then create ones and zeros out of it, right? In a specific order. So in order to do that, we need to go back to the values of each place. So you remember when we started with 1, then 2, then every time we just multiply by 2. So 4 multiplied by 2, that's 8. 8 multiplied by 2, that's 16. Then 32, then 64, then 128, then 256, right? So we keep doing this, and then we take that number that we want to convert, okay, and then we compare it to the values of these places. Following this operation here, you need to ask yourself, okay, what is the number? You go from the left to right, and then you ask yourself, the question is, which is the first number here that is less than or equal to the number that I currently have? So 256, is this less than or equal to 148? No, so ignore it. Then you move to 128. Is this less than or equal to 148? Yes. Okay, so this I'm going to put 1 here. If the answer is yes, you put 1. Then you subtract. You say 148 minus whatever the number that you put 1 under, which is 128. This is going to result in 20. Okay, now you take the 20 and then you continue the process. Is 20 less than or equal to 64? No, then you put a 0. Is 20 less than or equal to 32? No, you put a 0. Is 20 less than or equal to 16? I'm sorry, what I was, let's do this, maybe I said something wrong. I'm not sure if I said something wrong, so I will repeat that again. So when we start from the beginning, 148, okay, you ask if this number is less than or equal to the number that you are currently testing. So 148, we are testing 148. Question is, 128, is this less than or equal to 148? We said yes, and if the answer is yes, we put the 1, and then we do the subtraction. Then we are left with the 20, and then we keep testing the 20. Is 64 less than or equal to 20? No, so we put a 0. Then we move next. 32. Is 32 less than or equal to the number that we're testing, which is 20? No, then you put a 0. Then we move to the 16. Is 16 less than or equal to 20? Yes. Okay, so if you say yes, you put a 1. And then you subtract. Don't forget to subtract. So we subtract the 16 from the 20. Okay, that's going to equal to 4. Now we test the 4 and we continue. Is 8 less than or equal to 4? No, then 0. Is 4 less than or equal to 4? Actually, it is equal to 4, so answer is yes. So I'll put here 1. And then I subtract 4. 4 minus 4 equals 0. And then we keep testing. Of course, the 0 means that the rest are going to be 0. But let's keep testing. So we follow the same method. Is 2 less than or equal to 0? No, so you put a 0. Is 1 less than or equal to 0? No, then you put a 0. And that's it. Now you have your binary number from the left to the right, 1001, 0100. Don't believe me? No problem. We open the calculator. Okay, you can do it. You can start with a binary, or you can start with a decimal, whatever you want. I'm going to start with a decimal, and then I'm going to put 148. And then take a look at the binary thing. Let me make this smaller. So here's the number that we got, and this is the number that the calculator got. 1001, 0100, which is exactly what we got from this manual operation. Okay, so this is method number 1, the one that I like, And it's called the subtraction method because we keep testing and we keep subtracting and we construct the zeros and ones from answering the question, is this smaller or equal to, and so forth. However, there is another way, there is another method, and actually this other method, we call it the division method. And this is a more common one. If you go online and you search for it, you will find that the division by 2 actually is the more common one. But I don't prefer that one very much for two reasons. Number one, I don't like to do division. Okay. Number two, it does not involve writing the values of each place. You remember the 1, 2, 4, 8, 16. And maybe when I'm teaching binary, it is more important that you see these values over and over again to get acquainted and get used to them. But anyway, let's do the same exact number, which is 148. Let me use the blue. So 148, and let's convert that to binary using the second method, which is the division method. The division method basically says that you should divide by 2. So we take the number and divide this number by 2. Okay? So 148 divided by 2 is 74. Now you ask yourself a question. Is this 74? Is there a remainder? Like 148 is just 74. There's no remainder. There's no fraction here. So the answer is no. If there is no fraction, okay, you will put a 0, and I need you to see where do I put the 0 now. I will put the 0 to the right hand side. I'm not going to put the 0 here. For example, I'm going to put the 0 to the right. Okay? Then you keep repeating this. 74 divided by 2. So 74 divided by 2, that is 37. No fraction, because it's a even number, right? So even number divided by 2, there will be no fraction. So we put another 0. So is there a fraction? No. You put another 0. Then you divide by 2. But however, this time, because this is an odd number, so 37 divided by 2, that's 18.5. Is there a fraction here? Yes. So you put a 1. And you discard the fraction. This is important. So you put a 1. If you have a fraction, you put a 1. And then you discard the fraction. Okay. So what's next? 18 divided by 2. Okay. 18 divided by 2. Not 18.5. 18 divided by 2. You discard the fraction. That is going to be 9. Is there a fraction? No. Then there is a 0. You put a 0. And then you keep dividing. 9 divided by 2. That is 4.5. Okay. There is a fraction. I put a 1 and discard the fraction. Okay. 4 divided by 2. I'm sorry. This is divided by 2. And let me take this a little bit up. Okay. So 4 divided by 2, that's actually 2. Is there a fraction? No. Then I put a 0. And then I continue. 2 divided by 2, that is a 1. Is there a fraction? No. Then I put a 0. And then 1 divided by 2. So here I'm going to continue here. 1 divided by 2, that is going to be half. Okay, is there a fraction? Yes, you put 1 and then you discard the fraction. And then 0 divided by, when you reach 0 divided by 2, anything that is divided by 2, that's khalas, the end of the process. This is going to give you basically the same exact binary number, which is 10010100, the same number that we got from the previous method and from the calculator. Okay, very good. If you want to play around with the binary to decimal, decimal to binary, we can use this one. This is a website. I will put all the links in the description of the video. So all the links that I will be using today, I'll put them for you in the description of the video so you can open them and have fun. For example, here, this is a game, a light bulb game that was created by the CS50 team. And you can put here, as you can see, we have 1, 2, 4, 8, 16, 32, 64, 128. And this current situation which is turned on, turned on, turned off, turned off, turned on, turned off, turned off, turned off, or 1100101, I'm sorry, 000. That's basically equal to 200. Where did we get the 200 from? It's basically 128 multiplied by 1 plus 64 multiplied by 1 plus 0 plus 0 plus 8. If you do the math, it will come up to 200. So you can play around with this. You can put it in game mode. It will ask you about a number, and then you can convert it on your own. It's pretty fun. Okay. Now, if you think about what we just did, now, think about it. We solved our first problem when it comes to how are we going to use the computer to solve problems. So actually teaching the computer to solve a problem is a problem itself that we needed to solve, right? Because, okay, in order to solve problems, we need inputs and we need an operation and then a solution or an output. But you know what? How can we do this in the first place? So we have a problem to solve a problem, and the main problem was, how can we input information into the computer in the first place? However, if you think about what we just did, we actually succeeded in that. As I said, if you have a board, an electronic board, or electrical board that has series of circuits or series of lamps, or call them whatever you want to call them, but electrical circuits, okay? Or what we call transistors. And then, using the binary system, we keep switching on and switching off these circuits in a specific order. We can translate that to decimal. So, if you come to me now, let's take this example, very good example. You come to me, and then I have this electrical board with circuits, and each circuit has a lamp. And then I kept switching on and switching off. And then I didn't say anything. You came to me, and then I showed you this electrical board with these turned on and turned off lights without saying a word. Will you be able to understand the number in decimal that I am storing on this board? Actually, yes. So I was able to store a number on my computer or my electrical board, just simply connect electricity to it, turn on and turn off some switches, and I am able to store a number. It is in binary, but we can convert it to decimal. It's very easy, right? Even if you see that as my guest, you take a look at that, so you will understand what this means in decimal. So I was able also to communicate to you a number. Not only store it on the board, but use the board to communicate that number to you. So that's basically solving our problem into how can we input information into this computer that is using electricity. However, I know what you're thinking. Are you kidding me? Just numbers? But we don't want to just store numbers. We want to store other stuff. So how can we teach computers things other than numbers? How can we teach computers to store texts or pictures or videos? Okay. In order for you to understand this, you need to understand a very important concept that is called context and format. So we have the decimal system that we understand, and there is the binary system that the computer understands. The computer doesn't understand anything, but you know what? Like a car, we can assume that the car understands fuel. This is how it's designed. So we can safely assume that the computer understands binary. Okay. So computer understands binary, we understand decimal, and we can convert back and forth, so there's no problem. However, we have also letters, we have pictures. Okay, instead of inventing a system for each of this, which would be very hard to do, like to invent a system for each of these things that we want to teach the computer, we can just use the decimal system that we already understand. Okay, how can we do that? Using context and format. What do we mean by context? Using a decimal number in different contexts will mean different things. Okay, let me rephrase. Let's say, for example, the number is 65. Is this a number? Absolutely. Are you using it in a number context? What do you mean by a number context? If I'm using the number 65 in a calculator, that is a number context, right? On a calculator, what do you do on a calculator? You use numbers, you input numbers. So the number 65 will mean 65. But if I take that same number, 65, and use it, for example, in a different context, like a text context, this number 65 is going to mean a capital A. Why capital A? We'll talk about this in just a minute. But what I want you to understand here is that by defining different contexts, we can recycle, we can reuse the decimal system to mean different things. And we stick only to the decimal system, okay? One system to convert between it and the binary is just more than enough. So we will stick to the decimal system, and with the decimal system, we need to agree on a context. If the decimal system is used in the numbering context, it means what it means. It means numbers. But if we use it in the text context, for example, it means letters. If we use it in the picture context, it means pictures or colors, something like that. In order for you to understand better the context thing, let me ask you this. Can you use computers, right? Can you open a video in a calculator app? No. You have a video file. Someone sent you a video file, or you have a movie that you have downloaded from the internet. Can you open this movie in the calculator app? No, you can't. Can you open this movie in Microsoft Word? No, you can't. You have to open it in a movie program, right? Why? Because that's the context that this program understands. The program that displays or plays video, it understands binary in video context. So eventually everything is in binary, right? Or what we can convert later to decimal. So the computer, you need to tell the computer, what is the context of this binary? Okay, when I display the board to you, you remember the board that has these electrical signals? When I display this board in front of you, you will see binary, then you will convert it into decimal, but then you're going to stop. You're going to have the number 5. But then what does the number 5 mean? What does it mean? It means just 5 in this particular case. But what if I give you a signal, I hold the board, okay, same exact board with the same exact binary value, which converts to 5 in decimal, but then on top of the board, I told you, I put a sticker that says text. Then the same binary number converts to the same binary 5, but then you will understand that this doesn't mean 5. It means a letter, maybe the letter F or something. Do you understand what I'm saying? So that's the importance of this context thing, that we use binary or decimal, because we can convert back and forth. You use binary or decimal in different contexts, and they will mean different things. And then if we can do that, we will be able to teach computers stuff other than just numbers. Okay, what about the format? Actually, the format is the context, but specified, a more specific context that we agree on. And moments ago, I said that, for example, we have the letter A equivalent to 65, or actually, to be more precise, the decimal number 65 in the context of text should be converted into the capital letter A. And that actually, this is not an example, this is a fact. But why? Why 65 is converted to A? And this is the format. So in the text context, we humans needed to agree on different formats. And based on the format, we will do the translation like we do in Morse. You remember the Morse, the dash and the dot. Humans, they did sit together and they agreed, okay, if the dash, then a dot, that's that specific letter and this kind of stuff. It's just by agreement. This agreement, we call it the format. So let's take a look at some context and formats that we have. For example, we have the text, and text is the context. And in text, we have several formats like the ASCII, we have the Unicode, we have other stuff. And the ASCII, let me go ahead and open the ASCII table for you. So here we have the ASCII table. You see, this is a format of texts. A specific format of the context text. So, we started, humans, they did sit together at some point in time, and they decided, for example, as I told you, that capital A is equivalent to the decimal number 65. Why? There's no why. This is how they agreed, because they started with the null and then some symbols, and then as you can see, the exclamation mark, for example, is 33, and then they kept adding some more symbols. And by the time they are finished with symbols and numbers, and the turn was for the A, it was the number 65. They started from 0, and then when they reached 65, it was A. So it's just a coincidence. So there's no reason why A is actually 65. There's no like formula or something. This is how the table came when they agreed on it, and then that's it. Okay, what about Unicode? Unicode is just like ASCII, just broader, and we will talk about Unicode in just an example. So combining these together, combining the text and the format together, we get different types of files. Like for example, we have TXT files, the notepad files. So what is a TXT file? It is a text file using ASCII or maybe using Unicode or something like that. So if you bring a bunch of binary numbers and then put them in a file and save that file as a TXT, what you're basically saying that this is a text context, and then when you open the file, you will understand what's the format of that particular file. It's using ASCII, using Unicode, and this kind of stuff. We also have DOCX, we have RTF. These are different files. All of them are in text, but maybe they're using different formats. The same applies to pictures. So pictures, they are using different colors. So we paint colors, and then we come up with pictures. We have, for example, the RGB system, which is red, green, blue system. So we mix colors based on the shade of gray, shade of green, and shade of blue. Or we use the CMYK, okay? Or this is different from the RGB. CMYK stands for cyan, magenta, yellow, and black. So again, we can either combine these or combine these. So here we're using the red, green, blue. Here we're using the cyan or cyan. I'm not really sure. Doesn't matter. And the magenta, and then the yellow, and then the black. So two different ways of mixing colors, or two different formats in the same context, which is pictures. Again, if you combine these two, you are going to come up with some file types, like the BMP or the JPG or the GIF. And each one of them is a picture, but it's using maybe different formats or different methods of encoding for pictures. Okay, we have also audio. Audio, it has the volume, so we need to decide how are we going to represent volume using numbers. How are we going to represent the pitch of the sound using, again, everything here is using numbers. Okay, so ASCII using numbers, Unicode is using numbers, decimal numbers, eventually convertible to binary. The same thing here, RGB, we will see in just a minute how we use numbers here. CMYK, again, the same thing. Everything is eventually going to be decimal numbers, and from decimal numbers we can convert to binary, which is something that the computer understands. Also in audio, we have MP3, we have WAV, we have AAC, different file types using different formats in the context of audio. If we move to video is basically a picture sequence plus sound. So we have a bunch of pictures in a sequence plus audio. So basically videos are just combining these two together. And again, we have, this one should be MB4, that's a mistake, right? So MB4 AVI, and WMV. Okay, so these are file types, video file types. Again, based on numbers, based on binary things. So let's take an example. How about this example? This is a very good example. So I'm going to give you the context here, then the value, then the result. If we are in the context of binary, which is the basic thing that the computer understands, and then we have these three values here, and I divided these into 8 bits, each one of them. By the way, a bunch of 8 bits, we call it a byte. We will talk about this later, but just to keep it on a side note. So a bunch of 8 bits together, when we put 8 bits together, we call that a byte, okay? So I brought you 3 bytes, so 8 bits, 8 bits, and 8 bits, okay? And then I want you to tell me what is the result of translating these binary numbers. Of course, if you combine them all, they will become something like this. But I want to take them like each 1 byte at a time, okay? No pun intended. The byte here, not byte, B-Y-T-E, okay? Which is the 8 bits. But it can go 1 byte at a time. Okay, so 0, 1, 0, 0, 1, 0, 0, 0. Okay, so this is a binary. What does that mean? Okay, if you want to know what does that mean, you need to tell me what's the context. In a context of text using ASCII, you remember text and format. Context and format. So the context is text. I'm using the ASCII thing. So 0, 1, 0, 0, 1, 0, 0, 0. How is that going to translate into ASCII? Number one, I need to translate it to from binary to decimal first, and for that I will use the calculator. Khalas, we're not going to do this manually anymore. I know that you may be, you don't like the manual stuff, and I agree. You need to just understand how it's done, but later on in your real life, you will never, most probably, need to do it manually. Use a calculator. But you have to know how it's done, okay? So I will do that 0, 1, 0, 0, 1, then 0, 0, 0. Okay, if I do something like this, it seems like it's giving me the number 72. The number 72. Maybe I should have done something here to improve this slide, and then from binary, I can add here after binary another context. I will do that. I will improve this slide slightly, and then also add here the numbering system, because that's one of the contexts, right? Because we are in calculators, we use numbers as is, like as numbers. But okay, now I can convert this to the number 72. So the number 72. How is the number 72 going to translate to text? I need to open the ASCII table. So I can take a look at this ASCII table. I have another table here, by the way, so I like this one a little bit more. So let's take a look at this 72. So what is the number 72? As you can see here, let me zoom in a little bit. Yeah. So 72, it seems like it is the capital H. Okay, that's nice. So capital H, that's it. I already put it here. Capital H. Okay. What about this here? 0, 1, 1, 0, 1, 0, 0, 1. Okay, let's open the calculator and let's try that one. Binary. And then we do 0 on the left. We can just ignore that. Let's start from 1, 1, 0, 1, 0, 0, 1. I will tell you later why I intentionally put the zeros on the left. As I told you, I'm getting the numbers in bytes, and the byte is a bunch of 8 bits. So even if there are zeros to the left, I will keep them. But we will talk later about this. So 1101,001, that is going to be the decimal number 105. Okay, going back to the ASCII table, going all the way to 105. Okay, that is a small I. You see, 105. Forget about the number. This number here. This is in hexadecimal. I told you that we have multiple numbering systems other than the binary and decimal. We have hexa, we have oct and this kind of stuff. So forget about the 69 for now. We are interested in the 105. If you feel like you're going to get confused, just use this simple one. This one has only decimal and ASCII. So if you want to go 105, it's the small I in here. Okay, so that is a small I. Then we have the 001, 00001. Anyway, this is if we convert this using the calculator. So 1 and then 5 zeros. I'm sorry, I need to 1, 5 zeros. Then 1. That is basically, I'm sorry. Hold on. This is 4 zeros, I'm sorry. So 1, 4 zeros. Then 1. This is actually the decimal number 33, which is if you take a look at the decimal table, at the ASCII table in decimal, you will find that 33 is basically an exclamation mark. Okay, so if we do something like this, like we have a bunch of bits in bytes, and we convert each byte into ASCII, we are eventually going to get the high. So high. However, the same exact values, if we put them, for example, in the context of pictures, pictures basically use colors. How do we know? Because as I said, picture is a context, then the format is what we need also with the context. And the format that we will be using here is called RGB, or the red, green, blue color system. And the red, green, blue basically means that we will take the number, and this number is going to represent a shade of red or a shade of green, shade of blue, and then when we combine these three shades together, we will get our resultant color. If you want to do this, you can. I'm not going to do it now, but if you don't believe the colors, we can use this very nice website, and then you can put the numbers here. However, these numbers are in hexadecimal. This is the other numbering system that we were talking about. So you put the numbers here in hexadecimal. Okay. So for example, I will just do one for you. So we will open the calculator again. Okay. So let's say, for example, we want to do this. So I'm going to go escape 1001, then 3 zeros after that. So this is 72 in decimal. But in hexadecimal, that is 48. And this is the number that you need to input here, because this one is a RGB to hexadecimal. It's using hexadecimal. So the number what we came up with in hexadecimal, and don't worry about the hexadecimal for now. Okay, later on, we're going to have a detailed explanation of the hexadecimal system, because we will use it in CS50 later. However, that number in binary, which is 72 in decimal, is equal to 48 in hexadecimal. And if you go here and you put that 48, it's going to give you that shade of very dark shade of red. If you increase that a little bit, as you can see here, it's going to give you a brighter shade of red. So combining these shades together, so this shade of red and this shade of green, for example, and maybe a very good blue, it gives us this color. So combining different values of red, green, and blue, it's going to give us eventually that number. And these are in hexadecimal, eventually convertible to binary as well. Convertible to decimal, convertible. All the numbering systems can be converted back and forth between each other. Okay, so as you can see, the same number. So you can see this is a huge number in binary, but if we divide it into bytes and then we take each byte and then put it in its in a specific context, it's going to mean something different. So the same binary can mean high, or it can mean this very dark whatever color is that. That's a combination of these three colors here. Okay, very good. What about the emoji example? A very nice example that David discussed in his lecture about this emoji. Now, I'm sure that this is the most common emoji that is currently used on the internet. And this is what we call the the smiley face with tears of joy. Okay, now, can I store this or can I send it to someone using a computer? Yes. This symbol, we can just think of it as a symbol, very much similar to the A symbol or the B symbol. It's just a colorful symbol, more complicated symbol. But can I actually send this? Can I store this in a computer? Actually, yes, you can. Okay, we know that we can use ASCII, but if you open ASCII, you will find that ASCII is very limited. That's it. This is the ASCII thing. So the ASCII starts at decimal 0 and ends with decimal 127, and it has only very basic symbols, numbers, capital letters, small letters, and then that's it. What about the Arabic letters? What about the Chinese letters? What about emojis? Actually, we don't have this in decimal. We have to use a different format. You remember the word format. We have context. Khalas, we are in a text context, right? So you have the text context, but the format, we cannot use ASCII because ASCII is very limited, very simple. We can use, alternatively, we can use something that's called the Unicode. The Unicode is a different text format that we use in computers, and it has way more, it has a bigger, it accommodates a bigger bunch of symbols. So if you go here to this page, again, I will put all the links that I'm using in the description of the video. So this is a list of Unicode characters on Wikipedia, and as you can see, the page is really big. So we have lots of other stuff here. Then we have these symbols, and they have the code. This code is, by the way, in hexadecimal again. And I know that maybe you're wondering, why are you using hexadecimal? Why are you keep saying hexadecimal? We will explain that later, okay? There is a reason why we're using this hexadecimal numbering system. And it's pretty much the same reason why we moved from binary to decimal and later on to hexadecimal. So anyway, so here is the value in hexadecimal, which is, again, one more time, one final time, hopefully, it's convertible to decimal, convertible to binary. So here we have symbols. As you can see, you can keep scrolling, you will find letters, you'll find these symbols, for example, like the registered or trademark thing. Okay, so if you can keep scrolling, you will find some Latin characters. We didn't have that in ASCII. You keep going all the way, okay, and you will see also Arabic characters and other these Greek characters, for example. If you go all the way to the end, actually, I'm not going to do that. I'm going to use it from here. So if you go all the way to the end, you are going to find that we have in Unicode a special area for the emojis. So let's take a look at that. So here it takes us to emoji, but it has its own article. So let me open this article on Wikipedia. And here we have the emojis in Unicode. If you keep scrolling down, this is the Unicode part for emojis. So if you keep scrolling down here, you will find where did it go? Okay, let me scroll from here. So yeah, here it is. So as you can see here, here's the emoji that we're looking for. Okay, this is the face or smiley face with tears of joy. Let's open this article. And if you take a look here, you are going to find that this emoji is Emoticon's Unicode block, and it has the U+1 F602. This is, let me again zoom here a little bit. So 1F602, this is a hexadecimal number. Yeah, I know. F is a little bit weird here, but we will talk about that. Don't worry. Okay, and this is equivalent to 128,514 in decimal, by the way. So you don't believe me? You know what we do? The calculator, right? So I will open the calculator, and now I'm going to do the hexadecimal. And in hexadecimal, we can use letters. Again, I know it's weird, but just wait for it. It's coming later in a subsequent week. So let's do this. Let's reset. 1F 602, as you can see, it is converted here into 128,514. That's in decimal, and it has this very, very big binary number. So that's the thing, that we can, even this emoji, it can be converted into a decimal number, and from the decimal number, we can convert that into a binary, which is something that the computer understands. I know that you may be wondering about, okay, but no, hold on. This this face here is not just a symbol; it's a picture as well. So yeah, I agree. So when we work with computers, even the letter A, we need the computer to draw this letter A on the screen, right? So the letter A is actually used in two contexts. It's used in the context of text to store it into the computer. But then in order to display it on the screen, this A, that's actually a picture of the A. The same applies here. So if we zoom in a little bit into this one, we're going to see a bunch of pixels. If we take this square here between its eyes, you're going to see that it is actually a pixel. So we have these squares, and each one of them has a shade in this particular case, it's between yellow and black. But yes, so this emoji here is going to go into the computer in two different contexts, in two different channels. One of them as a character, as part of the Unicode, as part of text when you are writing the text using WhatsApp, for example, or Facebook Messenger or something of that sort. So when you are communicating it as text, it's using the Unicode code, which is this in decimal and this in binary. However, when we display it on the screen and with all these shades of blue and yellow and black and red, we need to convert that into a picture, and this is going to be translated into different numbers. Not these numbers, because as I said, the context is different, numbers are going to mean different things, and numbers themselves are going to change. Okay, now it seems like we have gone so far here. We now can store information into the computer. We can store here mean input. We can feed information into the computer, store it in the computer, maybe communicate it to other people as well. And we can output that as well on a screen using pictures and this kind of stuff. But this leaves us with the main problem of solving problem, as I said. We need to solve problems, but solving the problem itself is a problem. Solving a problem using a computer is a problem. When we solve problems on our own, that's actually okay, it's just a problem, we will just solve it. But now we want to do something extra. We want to solve the problem using a computer, and we seem to be faced by some obstacles. We passed through some of them, but now our problem, our real problem, is the box. So we were able to input, seems like we explained, using the binary and the Unicode ASCII stuff, RGB thing, and output is the same thing. Input and output are the opposite of each other. However, what happens inside the box is the thing. Now, if I say 1 plus 1 equal 2, okay, feeding a 1, feeding a plus, feeding another 1 into the computer, that's not a problem. We understand how we do it now, right now. But how are we going to teach the computer to add these two numbers together? That's what happens into the box. How can we teach the computer to say 2? How can we teach the computer to do even more complicated stuff? So feed computer with information, and then let the computer on its own apply a solution, and then give us the output. This is what we call an algorithm. So what happens inside the box is something that we call an algorithm, okay? And if you remember in my introduction to the course, the very first video, the introduction to the course introduction, I told you that the word algorithm is actually coming from the name of a Muslim mathematician and polymath. His name is Muhammad al-Khwarizmi, okay? So we take this al-Khwarizmi and then we convert it to algorithm. And this is different, as I said also, I believe I mentioned it in the course introduction video. Algorithm is different from logarithm. These are two completely different things. The logarithm, the one that you have on your calculator, this is a mathematical operation. It is like adding two numbers and this kind of stuff. This is not what we're talking about right now. However, we will come to the logarithm very shortly today in this video. But what I'm talking about right now is the algorithm. Algorithm means it's a way in order to think in a scientific way and solve problems efficiently. So achieve a solution on your own. Forget about computers right now. So if I ask you, for example, to come to my house, I invited you to my house, okay? There are several routes that you can follow, but you are going to think which one is the fastest route, or the one that does not have tolls, or the one that does not have any other problems like traffic accidents or something like that. So there are multiple ways to solve the problem, but achieving a good algorithm needs you to think in an efficient way and solve the problem in the fastest and the most accurate way. So the definition of an algorithm is how to think logically to solve a problem efficiently. Okay, so think in a logical way in order to solve the problem efficiently. When I say efficiently, as I said, means accurately and in a fastest way possible using the least amount of resources. Okay, now let's take an example. You remember when I told you that we have two methods of converting decimal to binary, right? I told you that we have the subtraction method, and I told you that we have the division method as well. And I already discussed both of these with you. One of them may be a little bit better than the other. I know in this particular example, maybe personal preferences are going to control the decision. But in other problems, you're going to find multiple solutions, and it's going to be evident, it's going to be clear that one of them is actually more efficient than the other. One of them is going to take us from point A to point B faster, like the example that I told you about if I invite you to my place. One route is going to always be faster than the other route. Maybe another route is going to be faster, but more expensive if it has tolls, for example. So this is the compromise that you will need to do, or that you will need, the decisions that you will need to make when it comes to algorithms, that we have several ways of solving problems, but you're going to choose the best one. The best one may be the faster one, maybe the one with less cost, stuff like this, or maybe something in between. So it's up to you to decide, but you have to decide scientifically, logically, okay? And this is all what we mean by algorithms. Like we said before, in order for you to teach babies, remember, teach babies how to solve a problem, you need to understand the solution yourself, right? So if you have your own child and you're teaching your child how mathematics in school, so he's still or she's still young and you are helping her with her homework, you need to understand mathematics, right? Before you can teach her how to add numbers or multiply numbers, you need to understand that yourself. And this is what we'll be doing initially, okay? Like we did in the decimal system, you remember when I told you, in order for you to input information into a computer, you need to understand the basics of these information first. You cannot teach a baby the basics unless you understand the basics. And now we move forward to solving problems, and the same theory applies. You cannot teach the computer how to solve problems unless you know how to solve problems yourself. So this is going to take us to how to solve this problem. So if you have a 1000 or a 1240, I know 1024, I'm sorry, 1024 pages, a phone book or a dictionary. Now you can assume any number. Why 1024? 24 in particular. I will tell you in just a minute. There is a purpose behind that, but you can assume any number, okay? 1,000 if you want to make it like even, 1,000, no problem. Now, this is a problem that we need to solve. And later on, you will know that computers, I told you already, not later on or anything. I already told you that computers are even worse than babies. Babies at least have brains. Computers, they don't have brains. Computers, they don't cannot read between lines. They cannot extract information on their own. You have to be very clear, very precise. So let's take this problem and then see how are we going to solve it in many different ways and compare these different ways or algorithms, as I told you. An algorithm is a way to solve a problem, and the best algorithm is the most efficient algorithm. So how are we going, if I give you now a dictionary and I ask you to search for the meaning of the word water, what are you going to do? I know you are going to say, no, this is easy. I'm going to like roughly open towards the end of the dictionary, right? Because you know that the W is at the end of the dictionary. And then I'm going to search, I'm going to see where the W is, and I'm going to move forward. Yeah, this is because you're human, right? And I told you, computers are not humans. They cannot do, they are not that smart. So we need to move like robots. If I give you a dictionary right now, and you are not a human, you are just a robot thing. You are open from the beginning. That's one way to do it. So we can do a page-by-page solution. Page-by-page solution means that I will open to the beginning, and then I will keep flipping one page at a time, one page at a time, all until I find the word that I'm looking for. Is this method accurate? Yeah, it is accurate, because eventually I will reach the page where the word water is, and that's it. End of the story. Now, how many steps do we need maximum in order to search a dictionary for any word? Worst case scenario, 1,200 steps, because each step we do page by page, right? And we flip, and then we go through the page, and then we move to the next page, and then we keep flipping. Now, the maximum, like if we are looking for the last word in the dictionary in the Z letter, so the worst case scenario is going to be 1,024 steps, or just 1,000 if it's a 1,000 page dictionary, right? Okay, so we will call this N. So what is N? N is basically the number of pages, and the number of steps here is going to be N. So I have 1,024 pages, and the worst case scenario is that I will need N steps to search N pages. Okay? So this method, a page by page, let's just remember that's in the worst case scenario is going to take N. Now, how about we improve the solution a little bit? How about we do 2 pages at a time? So instead of flipping 1 page at a time, we are going to just do them 2 pages at a time. This is obviously going to be faster, but it's not accurate, right? Why? Because maybe when you're doing 2 pages at a time, the word that you're looking for is actually sandwiched between these 2 pages, and you're going to miss it. Okay, so if you want this to be accurate, it's a good solution because it's faster. But in order for this solution to work, for this solution to be accurate, and remember that algorithms, they don't just need to be faster, they just need to be accurate as well. This is why we use computers in the first place, to be faster and accurate. So something that's not accurate, it's not a good solution, even if it's faster. So if we want to use the solution, which is faster, we need to make sure it's accurate. And in order for us to do that, we need to have a backstep option. Backstep option means that, okay, you do the 2 pages at a time, no problem. But you need to make sure that when you do 2 pages at a time to check, do you find the word that you're looking for? If the answer is yes, you need to ask yourself another, if the answer is yes, it's okay. If the answer is no, you need to ask yourself another question that we didn't ask in the page by page method, which is, did I miss it? Was it sandwiched in the previous page? If the answer is yes, you need to go do this one page back. You understand? So okay, no problem. Do 2 pages at a time, but ask yourself an additional question instead of, is the word here or not? An additional question would be, is it possible that I already missed it in the previous page? Do I need to go one step back? Okay, so in this particular case, this is faster, as I said. Here, maximum number of steps is 512, which is basically n divided by 2, because we're doing 2 pages at a time, right? So if we start with 1,000 pages, then the worst case scenario is 500 pages. But again, because I'm using this odd number that I will explain in just a second, the 1,024 pages, so half of that, half the number of steps that we used in the page by page thing. 512 steps instead of 1,024 steps, which is basically n divided by 2. N divided by 2 means that the number of the size of the problem, the number of pages total that I have, divided by 2 is going to give me the number of steps that I need to go through in the worst case scenario in order to solve this problem. A third, way better method is we take it half book at a time. Okay, now in this method, what are we going to do? You hold a dictionary, you're looking for the word water, right? And then you split that dictionary into half. So get the dictionary from the half and then split it into 2 halves. And then decide, is the word that you're looking for. So for example, if I just split it into roughly into the middle, I will be in the letter M maybe, right? Now you are currently at the letter M. Do you see the word water? Answer is no. But now you ask yourself another question. Is it in the left half or in the right half? And in this particular case, it's going to be in the right half because the W is after the M, which I'm currently at. So the W, the first letter of water, is going to be in the right half of the book. Okay, so what am I going to do next? Completely discard the left half because I don't need it, right? If I'm now sure that the word water is starting with a W in the right half, why do I need to look into the left half? So basically I can completely discard the left half. Okay, when I discard the left half, how many steps did I skip by doing this? Half of the steps. So I started with 1,024 pages or 1,000 pages, and only after one step I jumped half the distance. Do you understand what just happened? So I'm not only doing it 2 pages at a time, I'm doing it half book at a time. So I do half of the book. If it's not in that half, completely discard that and look into the second half. And then we keep doing this again. So I now have the right half. I will open into the middle, see what letter I'm currently at. Let's say, for example, the R. And I need to ask myself the same question again. Can I currently see the word water? Answer is no. Is it in the right half or the left half of the current? What is remaining? That's half of the book. I know it may seem like confusing at the very beginning. And this is why I actually encourage you to go and see David is doing this demo using an actual phone book, and he's actually splitting it into half. So I started with the whole dictionary, split that into half. Now throw that away into 2 halves, throw 1 half away, and I'm now left with only half. But then I'm going to split that half into 2 halves. So I'm now left with only quarter of the dictionary. And we keep doing this until we reach the word that we're looking for. Now, is this accurate? No, it also needs direction control to be accurate, because now when I split the book into halves, based on what am I going to discard half? I need to ask, I may discard the half that has actually the word that I'm looking for, which is not accurate. But in order for me to discard the correct half and keep the other half, I need to ask myself I need to have some kind of direction control. Should I go left or go right? However, Surprisingly, if you do this method, you need maximum 10 steps. Only 10 steps? Yes. Only 10 steps. If you start with 1024 pages, okay, you can, worst case scenario, you will need only 10 steps to search the whole dictionary. You don't believe me? Now let's take a look at this. You started with 1024 pages, right? You split that into half. So this is the first step, not this, the 512, right? So you are left only with 512. That's the first step. Second step, you are left only with 256. Third step, 128. Fourth step, fifth step, 6, 7, 8, 9, 10. 10 steps only, and you are done. Okay? If you're wondering how did we get the number 10 without counting like this, it's basically log to the base of 2 to n. And this is the log. This is not the algorithm. This is the logarithm. It's the opposite of the exponent. It's a long story. Forget about it right now. But anyway, if you want to make sure, let me use the calculator here. Okay, so now I'm moving to the scientific. So if I do 1024 and then I do the log base 2 equal, it's going to say 10. These are the number of steps. As I said, this is how we mathematically calculate it. We start with the size of the problem, 1024 pages. Log base 2, that number is going to give us the 10 that we already reached by just counting it. Okay, don't worry too much about the log thing right now. Later, okay. But this is how we mathematically reach the 10 from the 1024. And actually, you know what? This is the reason that I started with 1024 pages, because I wanted a number that I can easily split into halves without fractions. It makes the example more student friendly. Okay, but if you start, for example, with 1000 pages, it's very similar. So if we start with 1000, actually let me open the calculator one more time. If we start with the 1000 pages, okay, and then we do the log thing, so log base 2 1000 is going to go about 9.9 which is 9.9 steps, which is not 10 steps, whole 10 steps. And this is, as I said, why I used 1024, because it has number of steps without any fractions. Okay, so if we talk about algorithm efficiency, so now we have seen 3 different algorithms that we can use to solve this problem of searching a dictionary or searching a phone book. But obviously, as you saw, one of them is way faster than the other. So one is faster than the previous one, and then the last one is way faster than the previous 2. If you chart these different algorithms on a chart, let's take a look at this. So here we have the problem size. Think of this as the number of pages in a dictionary or a phone book. And here the time to solve, think of that in steps or seconds. Okay, the first algorithm, the one with n, we had 20. If we have 20 pages, that needs 20. So let's, and if we start, let me do use maybe the blue. Yeah. So if you start here at 20 and you go all the way here, okay, that is going to take you 20 steps or 20 seconds, correct? However, if you use the second algorithm, which is n divided by 2, the one that we do 2 steps at a time, or 2 pages at a time, if you take a look, the same 20 steps, if we go here, we intersect here, and this is going to take half the time. It's going to take only 10 seconds or 10 steps to finish the process. So obviously, the second algorithm is faster than the first algorithm. However, you need to keep in mind that we need this step or this option to go back 1 page in case we missed the word that we're looking for. Now, how about the last algorithm, the one that we said log to the base of 2n? it looks like this. Okay, and this is the beauty of this algorithm. This is way faster. Okay, the bigger the problem, okay, even if you have a very big problem, you can finish that in a very small amount of time or using very few steps. As you can see here, if we take a look at 2 and 20, the problem size 20 pages, go up, it's going to intersect here. This is roughly 4. Again, if you do this on, if you want to do this on the calculator, so here we do the 20 log. Don't forget to do the base 2 because this is log base 2, not just log. Okay, log base 2 equal is going to be roughly 4.3, as you can see from here. Okay, what about if we have very big problems? Like as you can see here, if you want to do 200 is not even this line goes like the continues like this. This one continues like this. If we have 200 pages, that would need 200 here, and it will need 100. 200 for this one and 100 for this one. But you know what? If you take a look at this log base 2n, the last algorithm, the one that we go half book at a time, this is going to take less than 8 seconds compared to 200, compared to 100, less than 8. It's about 7.6. Let me actually try this as well. So if we do 200, okay, log base 2 equal 7.64. Okay, so that's way less than 200 for the first algorithm, less than 100 for the second algorithm. So this is the beauty of this algorithm. And actually, this proves to you why do you need to think in an algorithmic way. Okay, thinking in an algorithmic way, it may save a lot of time and a lot of effort on the computer, and it's going to allow the computer to give you the results way faster. And this is, remember that this is the reason that we invented computers in the first place, right? I can solve the problem on my own, but I'm bringing the computer to do it faster than me. So I need to take a full advantage of that. I need to make sure that I teach the computer the most efficient algorithm that is going to give me the solution in the fastest way possible. If you're wondering how this is happening, let me actually very quickly get back to this. Now, why is this so efficient? Because this half book at a time, if you add, let's say for example, if we now decide to use a bigger dictionary, instead of 1,000 pages, let's say for example 2,000 pages. That means if you use the first algorithm, you are multiplying the time that you need. Correct? So 2,000 pages instead of 1,000 steps, that's going to be 2,000 steps. Okay, and the same applies actually even with the second algorithm, even if it takes half the time. But still, 2,000 pages instead of 500 steps, that's going to double the time, or double the number of steps to 1,000. So half the 2,000. However, if you use the last one, we're not doubling the time. We're just adding only one step. You understand? If we start with 2,000, or we start with 2,048, which is double this one, how many steps am I going to add here? Are we going to double the number of steps? No. Instead of 10 steps maximum, it's going to be 11 only. Just add one step. Why? Because after one step, you discard half of the book already. So you started with 2,000 pages. After one step, what do? You discard 1,000 and you are left with only 1,000. This is what we already had. So after one step, all are we left to do is just to perform the 11 steps. And again, if one more time, if you use a calculator here, 2,000, which is the double, 2,048, double this number. If you do the log thing, so log base 2 equal 11. Just 11 steps. Although this one is actually faster than this one, but both of them are weak. Both of them are slow, because when you double the size of the problem, you double the time. Okay? But in using this algorithm, no, things are way, way better. You keep doubling, and this is why we have this. Let me remove the ink. So this is why we have this graph here. You see, the more the problem here, it's like linear. Okay, the bigger the problem, the bigger the time. But here, the bigger the problem, it's very slightly bigger the time is going to become. Okay, now we understand that. We understand algorithms. We understand that we need to solve the problems first as humans using the best algorithm possible. But then, hold on, we still didn't answer the question, how are you going to teach the computer that? As I told you, the computer does not understand between the lines. So you need to break down the algorithm, assuming that you've reached the very good algorithm. You need to break down this algorithm into very, very simple steps. And then, like a baby, teach it to the computer in the simplest way possible. So let's go ahead and do that. Let's do the algorithm. You remember this last algorithm that we used, the one, the log n, the half the book at a time. Let's go ahead and write the solution in just normal language, our language, okay, in what we call pseudocode. So what is a pseudocode? The word pseudo means fake. It's not real. And the code is the code that we're going to use to speak to the computer with. Later on, when we're doing programming, we will be talking to the computer on what we call code. Okay, but before we can do that, we need to write this code in something in a simple form that we humans can understand. A very, very simple form that we humans can understand. This is what we call the pseudocode. Okay, now let's take a look at this pseudocode for searching a dictionary or a phone book for a specific name. First step, pick up the phone book. Okay. Then open to the middle of the phone book. This is what we agreed on, right? Okay. Then look at the page. So when you open the book or the dictionary in the middle, the first thing that you need to decide is that is the word that I'm looking for is currently here. So you need to look at the book, and then if the person is on the page or the word is on the page, here this is a pseudocode for the phone book, but the same applies to the dictionary as well. Same thing, right? So if the person that you're looking for is on the current page, khalas, then go. That's it, done. End of the story. Successful. However, it is possible that when you open in the middle, the person or the word that you're looking for is not here. So you remember we needed something. We need to have this direction control thing. So you need to ask your question. Else if. So if the person is not on the page, else if the person is earlier in the book, is it in the first half, the left half? If the answer is yes, open to the middle of the left half. So discard the right half and take the left half and repeat the thing. Open to the middle of the left half. And then go back to line 3. What was in line 3? In line 3, we said look at the page. Yeah, because every time you open in the middle of the whole book, the middle of the first half, the middle of the second half, and then we keep opening in the middle, opening in the middle. Every time you open in the middle, you need to look at the page to decide if the person that you're looking for is actually there. That's the main task, right? So it said here, go back to line 3. Okay. If I go back to line 3, look at the page, and then repeat that again. If the person in the page, cool, no. Else, if the person is earlier in the book, yes, open to the left half and this kind of stuff. But we have another possibility here. What if the person is not earlier in the book? What if it's later in the book? What if it's in the right half? Then we need to put another condition. We need to say, okay, if the person is later in the book, okay, open to the middle of the right half of the book, and then go again to line number 3, which is look at the page. So we're basically constructing this directional control. You open in the middle, okay, and then check for what you're looking for. If you didn't find it, you need to decide which half to discard. And after you discard, you basically repeat the same thing. You open whatever you have left, you open it in the half, and you keep repeating. right and left, decide, discard, open in the middle, take a look, and this kind of stuff. However, we put this in a way that, as you can see here, is very simple way, very specific way. Okay, we're not assuming that the computer can read between the lines and this kind of stuff. We need to be very, very specific. Okay. Previously, in previous years, David and his team, they used to do this very nice demo. They didn't do it they didn't do it this year about how to create a peanut butter and jelly sandwich. Okay, and they have this nice table, and it has all the tools and equipment that you need. It has a knife. It has the peanut butter, and then it has the jelly, and it has a spoon and this kind of stuff. And then they tell people to create or make the peanut butter and jelly sandwich based on instructions from another person, assuming that they are robots, not humans. And then, for example, when you say, hold the bread, okay, then I hold the bread. Then, for example, put the peanut butter. So the person in this particular case is going to take the whole peanut butter jar and put it on top of the bread. Doesn't make sense, right? To us, to humans, right? When you say put peanut butter to a person, to a human with a brain, he will assume that you logically mean that I need to open the jar and then I need to take a scoop of peanut butter, for example. But the computer doesn't understand that. This is logic that humans understand, but the computer will never understand something like this unless explicit instructions are given. Because it's just a piece of plastic. It's a piece of metal. Okay, so you need to give it instructions very, very precisely without assuming the intelligence of humans. Of course, when we're done with this, we can add a line here that says else quit. Else quit means that, halas, if maybe after all, the word or the person that I'm looking for is not in the dictionary or not in the phone book. So I need to give myself also the option to abort the whole operation if I search the whole thing and I didn't find anything. Okay, so what can we learn from here when it comes to algorithms? We can learn a lot of stuff. The first thing that we can learn is something what we call functions. So when you are creating algorithms, when you're teaching computers these algorithms, you will be using stuff like functions. What are functions? Functions are very simply orders. Like when you say here, pick up, that's an order. Open to, that's an order. Look at, that's an order. Call, open, quit, all these are orders. Let me give you a very good example here. So we take this example and then we compare it with my example, which is that if you are giving someone directions, so let's assume that you are I am inviting you to come to my house and you've never been to my house before. So I need to give you directions. This is a problem that we need to solve, and hopefully I will give you the best algorithm. I will guide you to follow the best route possible to my house. So what I can say drive on Sheikh Zayed Road. That's an order, right? So I'm telling you, okay, I know where you live, and I say, okay, drive on Sheikh Zayed Road. I'm assuming here that you live on Sheikh Zayed Road. Okay, so drive on Sheikh Zayed Road, that's an order, that's a function, right? If I say, for example, turn left, that's an order, that's a function, okay? If I say, take the third exit, that's an order, that's a function. So this is what we mean by functions. Functions are basically orders that we give the computer, do something. One more thing that we can learn from here is what we call conditions. Conditions means that it's like a fork in the road. It's a yes or no situation, okay? I'm saying if something happens, else if, okay. What's the difference between if and else if? If means if this happens. Else means, okay, if the first if is not happening, let me ask you another question, okay? And then we can have these series of else ifs, for example, if, okay, that's a condition. If it's not fulfilled, what if? So else if is just another way to say what if. So if, and then here I can say, what about the other if? If it's not fulfilled, what about another if? And this kind of stuff. So I can ask you multiple questions, yes or no questions, that we call conditions. Okay, these conditions are usually coupled with what we call Boolean expressions. So what are Boolean expressions? These are the expressions that we need to apply the condition to. They're named after a scientist. His name is Boole. Okay, so what are Boolean expressions? I'm saying if. Okay, if that's a condition. If what? What is the condition that you want me to fulfill? If the person is on page, this is a yes or no question. If yes, means that this Boolean expression is true or yes. And if it's true, means that the condition is fulfilled, means that we will do something based on this. But if this condition is not fulfilled, we will resort to the other if, which we call the else if. And this other if has another Boolean expression, which is, for example, the person is earlier in the book. That's different. Person is on page, that's one condition. One Boolean expression with a condition. Person is earlier in the book, that's different. Person is later in the book, that's different. So these are the three states. So if you're searching for a person in a phone book, you can only have three possibilities. Person is currently in the page that I'm looking at, or earlier on the book, or later in the book. Of course, there is a possibility that we quit, means that we didn't find the person at all. That's the fourth possibility. Okay, if we are to apply this to the driving example. Okay, so now I told you to drive on Sheikh Zayed Road. Okay, drive on Sheikh Zayed Road. Now I can say when or if you reach exit 50, take left. So here I'm asking you a question. I'm giving you a condition. Condition means that you don't take the exit unless it is exit 50. It's not just any exit. So you keep driving, and then you have this question in mind. Ahmad said, if you reach exit 50, take the exit. So that's a condition coupled, or it's a condition with a Boolean expression. If you reach, if is the condition, and the Boolean expression is this exit 50. So you keep looking, you keep driving, and looking, and asking yourself, this is exit 30, exit 40, exit 50, yes. If it's exit 50, I need to take the exit. So based on the condition and the Boolean expression that comes with it, you will execute a function, means do something that I ordered you to do, which is take the exit only if it is exit 50. Also here we have loops, okay? Loops means that you keep repeating something over and over again, okay? So for example, you take exit 50 and then you are on a different road, and this road has several roundabouts. So what I said to you is that, okay, if you reach a roundabout, keep driving. And if you reach a roundabout, keep driving. If you reach a roundabout, keep driving. So basically, I want you to keep driving straight if you see any roundabout. This is what we call a loop. Loop means that it's instead of saying this several times, I can tell you, okay, you are going to see 3 roundabouts. Whenever you see the roundabouts, keep driving. If I say this to you, I'm putting you in a loop. Loop means that you keep repeating something over and over again for a certain number of times. So you drive, and then you meet the roundabout. That's roundabout number 1. Then you keep drive. That's basically repeating the same operation over and over again. And then the second roundabout, and then so forth. All right? So this is what we call a loop. Go back to the line number 3. I'm taking back, I'm repeating. I'm telling you to basically repeat a specific order of business several number of times until something else happens. So what we have learned so far is in algorithms, We have functions, we have conditions, Boolean expressions, loops. We also have variables. Actually, the example for variable is very simple. You remember when I just told you, okay, as soon as you get the exit, you are going to come onto this particular road, and then you are going to find 3 roundabouts. The 3 is a variable. So I will put you in a loop for a certain number of times. This certain number of times is what we call a variable. Okay, variable means it's a number that you can use for multiple purposes. One of them is to execute a loop certain number of times. We also have threads doing several stuff at the same time, events. We will talk about these later on. Okay, that's pretty much it. This was the first video of week 0. Thank you very much for watching. This was CS50x by Ahmad Said. Bye-bye.